Hello students, good morning. Welcome to this class, and in this class we study about the module 2. That is in the yesterday class, in the module 1 we have studied the basic aspects of power quality. So what is power quality, definition of power quality, what are short time voltage distortion, long duration voltage distortion, etc. So here we study about the analysis of power quality problems, and so what are the different techniques used like total harmonic distortion, TIF, and power quality cost evaluation, harmonic sources, like that we study somewhat in depth. So for that we need to follow the IEEE guidelines, standard recommended practices. So first of all we study about the mechanism of harmonics generation. So how the harmonics is generated in the power system. Okay, so this is what we study in this mechanism of harmonic generation. So mechanism of harmonic generation. So electricity generation is normally produced at constant frequency of 50 Hz or 60 Hz, and the generator CMF can be considered practically sinusoidal. So here we can see the sinusoidal frequency, this one, sinusoidal. So this will be your generated frequency. But what happens to the harmonics? Harmonics is this fundamental frequency which we have now is called as the first order harmonics. That is first order harmonics. Fine. So if you are having third order harmonics, then this same cycle will repeat 3 times in this time frame, that we call as third order harmonics. Okay, then if you are having the second order harmonics, that same frequency will repeat 2 times, that is first, second, and like that. So if you are having fifth order harmonics, the same frequency will repeat 5 times. Okay, so in this, like within this time frame, so the time frame will not change, but the time period of for a single cycle will change. I think you are getting this, what I mean going to mean, that is the time frame for this one will not change, that is time for single cycle will change. So in this time frame, in this 0.02 second, we are having the 5 cycles, but for a single cycle the total time required will be 1 by 5 into 50 Hz, that is 1 by 250 Hz. Okay, that is the time period for single cycle. Okay, so this a source of sinusoidal voltage. So electricity generation is normally produced at constant frequency 50 Hz or 60 Hz, and the generator's EMF can be considered practically sinusoidal. However, when a source of sinusoidal voltage is applied to a non-linear device, so if you are applied a sinusoidal voltage, that is an sinusoidal voltage to a non-linear device. So what are the non-linear devices? That is power quality devices are called as non-linear device, that is Thyristor, SCR, etc. The resulting current is not perfectly sinusoidal. So resulting current, that is once if you apply a voltage, then what happens? These non-linear devices will draw the current, and this current will be having some harmonics. These currents will cause us some harmonic. This current will be varying. This current consumption may vary, like your induction motor, like that is in the induction motor, say squirrel cage induction motor, the starting current will be very higher, then after that it will be normal, right? So same thing happens for slip ring induction motor also. In the slip ring induction motor, the starting current will be very higher, and then after 2-3 seconds it will be normal. Like that, in a non-linear load, what happens? The starting current or the current at a particular time at which it received from the received by the load, consumed by the load may not be linear. The current consumption of the load may not be linear, so it will be varying with respect to time. So that is how it produces the voltage drop. That is also the variations in the voltage drop. So voltage drop it produced also will be distortion. It causes the distortion. So what do you mean by voltage? Voltage is the multiplication of current into resistance. If the current is not consumed linearly, then the voltage produced will be having the distortion. Fine. So a source of sinusoidal voltage is applied to a nonlinear device or load. The resulting current is not perfectly sinusoidal. In practice, the presence of system impedance, this current causes a non-sinusoidal voltage drop and therefore produces a voltage distortion at load terminals, that is later contains harmonics. So that voltage contains an harmonics. അതായത് ഇപ്പോൾ ഒരു നോൺ ലീനിയർ ലോഡാണ് നിങ്ങൾ ഈ കണക്ട് ചെയ്യുന്നുണ്ടെങ്കിൽ ആ നോൺ ലീനിയർ ലോഡിൻ്റെ കൺസംഷൻ കറണ്ട് കൺസംഷന് അത് ഈ വോൾട്ടേജിന് ലീനിയർ ആയിട്ടുണ്ടാവുള്ളൂ. അതായത് ആ ഒരു കറണ്ട് കൺസ്യൂം ചെയ്യുന്നത് ചില സമയത്ത് കൂടും, ചില സമയത്ത് കുറയും. അപ്പോൾ ആ സമയത്ത് എന്ത് ചെയ്യും, നമുക്ക് വോൾട്ടേജ് നമുക്ക് കറക്റ്റായിട്ട് 1 per unit നമുക്ക് ഒരേ കോൺസ്റ്റൻ്റ് ആയിട്ട് വെക്കാൻ പറ്റുമോ? ഇല്ല. ചിലപ്പം വോൾട്ടേജ് കൺസംഷൻ കൂടും, ചിലപ്പോൾ വോൾട്ടേജ് കൺസംഷൻ കുറയും. സോ അതാണ് ഇവിടെ പറയുന്നത് വോൾട്ടേജ് ഡിസ്റ്റോർഷൻ. ഇറ്റ് പ്രൊഡ്യൂസസ് എ വോൾട്ടേജ് ഡ്രോപ്പ്, sinusoidal voltage drop, therefore causes a non-sinusoidal voltage drop എന്ന് പറയും. Okay. So next we see about to provide an intuitive view of this phenomena. So നേരത്തെ ഞാൻ പറഞ്ഞ കാര്യത്തിന് കുറച്ചും കൂടെ ഡീറ്റെയിൽ ആയിട്ടാണ് ഇവിടെ പറയുന്നത്. Intuitive view of this phenomenon, let us consider the circuits of figure 1.1 where the generator G is feeds a purely resistive load Rs plus J into Xs. This resistive load on through a line with an impedance of resistive load RL. Resistive load RL ആണ്. ഇത് ഈ ലൈൻ ഇംപിഡൻസ് RS plus J into XS. RS പറയാൻ കാരണം ഇത് സീരീസ് റെസിസ്റ്റൻസും ഇത് സീരീസ് റിയാക്ടൻസും ആണ്. അപ്പോൾ അതുകൊണ്ട് RS plus J into XS and a static converter, this one, static converter. So here what happens, here it is the total generating power is being utilized in the load. മൊത്തം ലോഡിൽ യൂട്ടിലൈസ് ചെയ്യും. ഇവിടെ എത്രമാത്രം ജനറേറ്റ് ചെയ്യോ അതിൽ ബഹുഭൂരിഭാഗം നമ്മൾ ലോഡിൽ യൂട്ടിലൈസ് ചെയ്യും. പക്ഷേ കുറച്ച് എവിടെ ലോസസ് ആയിട്ട് പോവും, ഈ സ്റ്റാറ്റിക് കൺവേർട്ടറിലും ലോസസ് ആയിട്ട് പോവും, പിന്നെ കുറച്ച് ട്രാൻസ്മിഷൻ ലൈനിൽ ലോസസ് ആയിട്ട് പോകും. സോ അതാണ് PS1 അതാണ് PC1. സോ ഈ PC1 ലോസസ് ഈസ് ഡ്യൂ ടു ദി നോൺ ലീനിയർ ലോഡ്. സോ these losses is the main culprit to produce your harmonic distortion. ഈ ലോസസ് ആണ് മെയിനായിട്ട് നിങ്ങളെ ഈ ഒരു സിസ്റ്റത്തിൽ നോൺ ലീനിയർ ഹാർമോണിക്സ് ഉണ്ടാക്കുന്നത്. എന്ന് വെച്ചാൽ ഈ PC1 പറഞ്ഞിട്ടില്ലേ, ആ ഒരു ലോസസ് ആണ് ഇതിൽ ഉണ്ടാക്കുന്നത്. സോ നോക്കുക, ഇത് PG1 പറഞ്ഞ മൊത്തം പവർ ജനറേറ്റഡ് ആണ്. അത് മൊത്തം ബഹുഭൂരിഭാഗവും നിങ്ങളെ റെസിസ്റ്റൻസ് ഇൻ ദിസ് RL it is consumed as PL1. But some of this one is being absorbed in PC1 and most of them is being is there in a transmission line losses, that is PS1. So this we study here. The generator supplies a power PG1 to the point of common coupling. So this one, point of common coupling is PCC of the load with other consumers. So this one figure shows the most of this power PL1 is transferred to the load, while a relatively small part PC1 is converted to power at different frequency in the static converter. Is converted to power at different frequency. Different frequency means that is non-linear load. Non-linear load. ഇത് ഡിഫറെൻറ്റ് ഫ്രീക്വൻസിയിൽ ഇത് പവർ കൺസ്യൂം ചെയ്യും. ഇത് ഈ സ്റ്റാറ്റിക് കൺവെർട്ടർ. Static converter will consume power but not in a same frequency but at a different frequency. Okay. converter to different frequency in the static converter. Besides, there is some additional power loss PS1 at the fundamental frequency in the resistance of the transmission line, transmission and generation system. So this is the fundamental frequency loss. So this we call as normal losses in the transmission lines. So this PC1 is the losses in the converter caused due to the nonlinear load, that is at different frequency. So the figure 1.1b illustrates the harmonic power flow, as the internal voltage of the generator has been assumed perfectly sinusoidal. The generator only supplies the power at a fundamental frequency, and therefore the generator EMF is short circuited in this diagram. Generator EMF RGH J into XGH ആയിട്ടാണ് ഇത് ജനറേറ്റഡ് EMFൻ്റെ ഒരു ഇത് നമ്മൾ എന്താ ചെയ്യുന്നത് വെച്ചാൽ ഇത് ഒരു റെസിസ്റ്റൻസും പിന്നെ ഒരു കറണ്ടിൻ്റെ മോഡിൽ ഇത് നമ്മൾ കൺവേർട്ട് ചെയ്യും. നേരത്തെ ഉണ്ടായത് വോൾട്ടേജും ഈ മോഡിലായിരുന്നു, അതിനെ ഈ മോഡിലാക്കി കൺവേർട്ട് ചെയ്തു. കൺവേർട്ട് ചെയ്യുമ്പം ഇത് RSHും XH ഉണ്ടായി, ഇത് ഷണ്ട് റെസിസ്റ്റൻസ് ആയി. I think you know about the converting the voltage circuit into a current circuit. So this is converted. So here we get RGH plus J into XGH and RSH plus J into XHS. So this is that is harmonic impedance, RSH plus J into XHS and RGH plus J into XGH. So this is equivalent impedance of that generator, and this is equivalent impedance of the transmission line. So this IH is the harmonic current that consumed by the converter. So and PLH, we can see P1H is the power which is consumed by the RL load respectively. In this diagram, the static converter appears as a source of harmonic current. A small portion of fundamental power PC1 is transformed into harmonic power. Sum of this power PSH plus PGH is consumed by the system RSH. So this one, sum of this PSH plus PGH. So this PGH is consumed by the RSH and the generator resistance RGH. So this power PGH and PSH, sum of this power is being consumed in the resistance RSH and RGH resistance, and the rest PLH in the load. So sum of this power is being consumed in the RSH, RGH and RL. And the harmonic power caused by the presence of the converter. Thus the total power loss consists of fundamental frequency component PS1 and the harmonic power caused by the presence of the converter. So the total losses is nothing but the losses in the transmission line, losses in the generator and losses in the load. So that is PSH, PGH and PLH. So we can see here the total generated power is being consumed here, and some of this one is being consumed in the static converter which is of non-linear, and this one, what are the total generated harmonic power is there, it is being consumed in the RSH and RGH and PSH. I think you got this one, source of harmonic current. So this IH is the source of harmonic current, a small portion. So some of this source will go to the RSH, some of the source will go to the RGH and some of the source will go to the RL. That is, the static converter will become the source of harmonics, and this source of harmonics, from that harmonics it will go, അതായത് അതൊരു സോഴ്സായി മാറും, അത് ഹാർമോണിക്കിൻ്റെ ഒരു സോഴ്സായി മാറും. ആ സോഴ്സിൽ നിന്ന് ആ ഹാർമോണിക് കറണ്ട് അത് എവിടേക്കാണ് പോകുന്നത്? അത് പോകുന്നത് ജനറേറ്ററിലേക്ക് പോകും, ട്രാൻസ്മിഷൻ ലൈനിലേക്ക് പോകും, പിന്നെ ലോഡിലേക്കും പോകും. സോ അതാണ് ഈ ഒരു ഡയഗ്രം കൊണ്ട് നമ്മൾ മനസ്സിലാക്കേണ്ടത്. So next I think you know about the fundamental frequency sine equation. Vt is equal to Vm sin omega t, and Vm is equal to peak value or maximum, and W is the angular frequency. Fine. And we know that Vt is equal to Vm sin omega t plus theta. Here we can say that the phase function is theta degree to left shift for a inductive load, and it is for right shift for a capacitive load. Okay, and we know that Vrms is equal to 1 by root 2 into Vp. Vp is the Vm, so Vm is equal to root 2 into Vrms. So Vrms is equal to Vm by root 2. Okay, so for more rigorous interpretation of the conversion mechanism, let us consider the case of the figure where V is the source voltage. V is the source of sinusoidal voltage, and E is the constant EMF of a battery with negligible internal resistance, and a thyristor turns on at omega t is equal to alpha and off at omega t is equal to beta. See here, the thyristor turns on or omega t is equal to alpha, this turns on, and omega t is equal to beta, it turns off. At omega t is equal to alpha, it turns on, and at omega t is equal to beta, it turns off. Okay, and its voltage drop during construction is neglected. During the conduction is neglected, the voltage drop in thyristor is not being considered here. So this is the thyristor voltage, source voltage, and it is the voltage at the load side, VA. So figure 1.3 ABC. So this one A, this fundamental frequency, B, here we can see the thyristor conduct, and then it will not conduct. So it will be conducting. So after this time only it will conduct, and after this time it will not conduct. So this is the total conduction time. Displays the respectively source voltage, the voltage across the thyristor, and the load voltage. Voltage across the thyristor and load voltage, while figure 1.3 displays the current waveform. So this is the source voltage, voltage across the thyristor, and load voltage. Vt is the voltage across the thyristor, that is thyristor is being turned on at alpha, it is turned on, and at beta it is turned off. Once it is turned off, there we can see these remaining waveforms. So it is turned off, then it is being conducted here, and this portion is of the next cycle and other portion. So the load voltage VA can be replaced by the three components as shown in figure 1.4 derived from the Fourier transformation. That is, VA can be replaced by V fundamental frequency, Vt, and VA. So that is VA is equal to VA1, VAH, and VA0. So this is derived from the Fourier transformation. VA is the fundamental frequency, VA0 is the DC component, that is constant, VA1 is the fundamental frequency, and VAH is the harmonic frequency. So source voltage is equal to fundamental frequency plus harmonic voltage plus constant voltage, that is DC component. So these three is to be considered. So it is derived from the Fourier transformation. So source voltage VA is equal to VA1 plus VAH plus VA0. That is load voltage VA can be replaced by these three components. So next we have VA1 is equal to root 2 into VA1 into sine of omega t plus theta 1. So theta 1 plus theta 1, how it caused plus theta 1? It is of inductive load, then that is why it is plus theta 1. It's a fundamental component VA1. Fundamental component means what? Fundamental component means, see, this is the fundamental component. This is the fundamental component, and that is of this VA1, root 2 into VA1 sine of omega t plus theta, and VAH, that is sigma h is equal to 2 to n root 2 VAH sine of h into omega t plus theta h. So this is of harmonic component. Harmonic component is what? It is of the thyristor on and off. During the on and off of the thyristor, this thyristor will consume current non-linearly. അതായത് കറണ്ട് ചില സമയത്ത് ഓൺ ആകുമ്പോൾ മാത്രമേ കൺസ്യൂം ചെയ്യൂ, ഓഫ് ആകുമ്പോൾ കറണ്ട് കൺസംഷൻ ഉണ്ടോ? ഇല്ല, കറണ്ട് കൺസംഷൻ ഉണ്ട്. അപ്പോൾ അത് നോൺ ലീനിയർ ആയില്ലേ ലോഡ്. അപ്പോൾ അങ്ങനെ വരുമ്പോൾ എന്ത് ചെയ്തു? ഒരു ഹാർമോണിക്സ് ഇൻട്രൊഡ്യൂസ് ചെയ്തു. സോ അതാണ് VAH എന്ന് പറയുന്നത്. സോ അത് നമുക്ക് h ഇൻറ്റു ഒമേഗ ടി പ്ലസ് തീറ്റ എച്ച് എന്ന് വരും. is the harmonic content, and VA0 is equal to 1 by t into 0 to t VA dt, that is VDC, that is DC component. അപ്പോൾ നമുക്ക് എപ്പോഴും അറിയാം ഒരു ഫോറിയർ ട്രാൻസ്ഫോർമേഷനിൽ നമുക്ക് എന്ത് ചെയ്യും? ഒരു കോൺസ്റ്റൻറ്റ് പ്ലസ് VC എന്ന് പറഞ്ഞ് കൊടുക്കൂല്ലേ, പ്ലസ് C എന്ന് പറഞ്ഞ് കൊടുക്കൂല്ലേ. ആ പ്ലസ് C ആണ് ഇവിടെ VDC എന്ന് ഇവിടെ കൺസിഡർ ചെയ്തത്. അതാണ് DC component. Equally, the current can be replaced as I1 is equal to root 2 into I1 sin omega 2 plus zeta 1 plus and IH is equal to sigma n h is equal to 2 to n root 2 IH sin h omega t plus zeta h. So we can see the load voltage VA1, VAH, this load is being consumed, this VA1, VAH and VA0. This is all consumed in the load. So next we are having the I0. I0 is equal to what? VDC minus E by R. So I0 is equal to VDC. VDC is the DC voltage minus E is the voltage in the resistance, in this resistance. VDC, this one, by R is the resistance, this resistance. So next let us consider the energy aspects. The active power generated by the source is Pg is equal to V1 I1 cos zeta 1. So V1 I1 cos zeta 1. So we know that we know the fundamental frequency of the fundamental current. So that is I1 sin omega t cos sin omega t plus zeta 1, that is cos zeta 1. That is sin of omega t plus 90 is equal to cos theta. Sin of omega t plus theta is equal to cos theta. So like that, sin of omega t plus zeta 1, that is cos zeta 1. So V1 I1 cos zeta 1. So this is fundamental in case of power. So the next, the total power is fundamental power, harmonic power and DC component. So fundamental VA IA1 cos of theta minus zeta 1. Theta minus zeta 1 is equal to I1 square into R. So this is, so what do you mean by losses? What do you mean by power? Power is the losses. Losses can be represented in I square R. So that is I1 square into R. This is the power supplied to the fundamental component. So that is PAH. Similarly, we can represent it as VAH into IH cos of theta h minus zeta h, that is equal to h is equal to 2 to n IH square into R. IH square is a harmonic current. Harmonic current, losses caused due to the harmonic current. Similarly, is the power supplied to the harmonics, that is in case of DC we are having VDC into I0. VDC into I0, that is equal to E into I0 plus I0 square into R. So is the DC power. So this we call as the DC power. Therefore the thyristor behaves like an energy converter. Thyristor behaves as an energy converter. The ideal voltage source combines with the fundamental component of the current waveform to generate the total power Pg. The ideal voltage source combines with the fundamental component of current waveform to generate the Pg. So Pg, both of them will combine. So as the thyristor losses have been ignored, Pg is equal to Pa. Pa is the fundamental, is the load power, and generated power is equal to the load power. So if the losses are being is ignored, whatever we generate, it is being consumed. And the following relations can be applied, that is Pg is equal to Pa, that is I square into R plus E into I naught. So if we ignore this both of them, then if we ignore the losses, then this should, the fundamental losses, the losses caused due to fundamental harmonics and losses caused due to the third, fifth and seventh harmonics should be ignored. Fine. Then we can have Pg is equal to Pa, that is equal to I square into R plus E into I naught, where I is equal to root of I0 square plus I1 square plus root of H is equal to 2 to N IH square. So what is the total current here? Current in the resistance, the current is equal to the DC component, then fundamental component and harmonic component. That is it is the root mean square of RMS value. Okay, so this is what about in this class. So if you have any doubt, please feel free to ask me.